Hello everyone. So we continue with learning theories. So this slide gives you a rough overview about some of the theoretical approaches to understanding the performance of machine learning. So we can start maybe the bottom top right, which is the corner of the classical statistics, or also called frequentist statistics. So yeah, it rejects the idea or the mechanism of a prior probability. It's the dominant approach in the last century and today. So key values or key persons are Fisher, who invented the p-value or defined the p-value, Pearson and Nyman, definition of confidence intervals, hypothesis testing. So if you study statistics, you hear a lot about these issues. Then below is what I call algorithmic statistics. Here the focus is more on prediction, like in machine learning, not as much on parameter estimation as in frequentist statistics. So some names here are Leo Breiman, Friedman, Huber, and also Trevor Hastie. So they take a bit more modern view on statistics and sort of take a big step towards machine learning, if you want to look at it in this way. And if you look at the book from Trevor Hastie, which I recommended, you get a feel for how these people think and act. Yeah, then another subfield is robust statistics, where essentially you assume non-Gaussian likelihoods. For example, Laplace likelihoods, and you're attempting to be less sensitive to outliers, for example, whereas the Gaussian noise assumption is typically leads to models which are more sensitive to outliers. So on the opposite side, bottom center, bottom left, you see the Bayesian approach. Bottom left, you see the subjective Bayesian statistics, which is the most consequent way of doing Bayesian statistics. And the basic assumption is that subjective knowledge can be formulated and should be formulated as probabilities and can be integrated into statistical modeling. And we discussed some of the advantages and disadvantages of a Bayesian approach. So it has a lot of advantages, particularly it's a complete probabilistic model. You have to make statements about all the uncertainties in your model, but in practice it's a little bit difficult to handle, and sometimes you need to have pretty complex approximations. You end up with integrals you have to solve in some way. Then objective Bayesian statistics was an attempt to work with the Bayesian approach, but make the prior assumptions as weak as possible by defining so-called non-informative priors. Jeffrey was pushing this direction of research, or maximum entropy priors can also be looked at in this way. Another approach is to say that maybe not all hyperparameters should be just integrated over, which would be the Bayesian approach, but some hyperparameters like the noise variance and the regularization parameter can also be estimated from data. That's the so-called empirical Bayesian approach, sometimes called type 2 likelihood approach or evidence framework. So that's a little bit going in the direction of a frequentist approach, but it's still a Bayesian view on things. Then on the top left, you see the VC theory, or also called statistical learning theory, and VC stands for Wapnick and Chervonenkis. They're making no assumption on the function, on the underlying function, whereas most other approaches sort of implicitly assume that the true function is among the functions under consideration, and it has had a lot of impact in the time when neural networks were not very popular, so maybe the late 90s and maybe 2010. It led to was the basis for the construction of the kernel machines and the support vector machine. So it also had practical impact, and we will briefly discuss it today. Quite related to VC theory is PAC learning, where PAC stands for probably approximate correct. A lot of things are quite similar to VC theory, but it also considers computational complexity. A proponent here is Valiant, who also received the Turing Award for PAC learning. And in the middle are some things which don't really maybe fit somewhere nicely, or something which doesn't fit into one of these corners. So there's regularization theory, which says that one should have estimators which have some sort of stability, or should be regularized. So one should always try to make an ill-posed problem into a well-posed problem by using regularization or stabilizing penalty terms. Hadamard and Tikhonov are two people in this corner. Then on the right, empirical risk minimization is a term introduced by Wapnick for approaches which essentially minimize the training error. Then there's the least squares principle, which says squared error should be minimized and can be motivated by a Gaussian likelihood model. And Gauss was, in fact, the inventor of the least squares principle. Then MDL theory is stands for minimum description length theory. So it's derived from information theory, but it's very close to empirical Bayes evidence framework. And the people who are, or the names which are associated with MDL are Risanen, Wallace, and Boulton. So some people, it's a relatively small community, but some people prefer this view on the world, which is absolutely okay. But technically, it's very close to the Bayesian evidence framework. Function approximation we discussed before, which is not really a statistical theory, but of course you want to have functions which give you good fits. So it doesn't really help you to have low uncertainty in your model if the model is completely incorrect. And we discussed function approximation before when we discussed the complexity of functions in terms of number of basis functions you would need, or degrees of freedom you would need. And then I also included probability, which is really a mathematical theory, but sometimes you can derive, let's say, an optimal estimator based on some theoretical assumptions, and then in these estimators there are some things you can, like a mean or covariance, which you're able to estimate from data, and then if you estimate it from data, you are also doing statistical modeling. But the main corners, I would think, is the frequentist approach, or the classical statistical approach, the Bayesian approach, and then maybe VC theory if you're for machine learning. So we will cover classical frequentist approaches, particular CP statistics and archaic information criterion, AIC. Then we talk about the Bayesian approach, whereas the strict Bayesian approach does not really do model averaging. It doesn't do model selection, it does model averaging. So in your prediction, you should consider all models which seem plausible to you. But there are also methods to do model selection, and one is the Bayesian information criterion, or BIC. And finally, modern frequentist approaches. Briefly mention the MDL principle, and then talk a little bit more about statistical learning theory, or Vapnik-Cherevenko's VC theory. But let's start with a classical frequentist approach. So we are interested in the training error, which is the cost on P of xy based on the W hat, which was optimized on the training data. And then we want to average over all training data to be independent on the particular training data set. So we essentially are assuming evaluating a particular model M and not a particular parameter vector, because we are averaging over all training sets, and each training set would give you a different parameter estimate. There's something which is strictly only limited to models where you minimize the squared error, but it gives you insight in general into learning, and it requires only more or less machinery we are able to manage in this lecture. So we assume a fixed but unknown P of x, so the input is unknown but a fixed distribution, and y is a function of x plus epsilon, where epsilon is uncorrelated uniform noise. No, not uniform, but uncorrelated noise, independent noise. So it's uniform in the sense, uniform is right. So it's independent of the input. Anywhere on input we have the same type of noise, and the noise is uncorrelated. So if you know the noise in one location, it doesn't tell you anything about the noise in another location. And if we use the quadratic cost function, we can decompose the quantity we are interested in. So the evaluation on the test data of the model which was trained on the training data, average over all possible training data, can be decomposed into three terms, and that's the square of the bias, plus the variance, plus the residual. So that's the famous bias variance decomposition. And then, so if you can estimate or get statements about these three terms, we can estimate the test cost. So the residual is simply the cost of the true model. So the true model gives you the best test set performance, but it cannot predict the noise on the data. So it's simply the noise variance sigma squared, and you can also define it as the squared difference between your prediction of the true model f of x minus y, and then you average over the data p of x y, and you can also write it as a quadratic cost of the true model f. So in regression, which we're considering here, is simply the noise variance sigma square. So this is the noise. The bias is the mean square of the difference between the true model and the average prediction of all models trained with different training sets of size n. So n is fixed. So for example, a regularized model would be biased, or a linear model is biased if the true model is quadratic. So if you have structural bias, you're picking the wrong model. And we define m of x as the expectation over all training data of the prediction of the model based on the estimate on the training data. So the bias square is simply the integral over this function m of x, which is sort of the mean of all estimated functions, minus the true function squared and then averaged over all input data x. Well, we don't have to average over y because that's already in the mean function hidden. So that's called the bias. And some models are unbiased, some models are biased. I think we discussed this before. Then there's the variance, which tells you how much the functions trained on the different training data vary around the mean function. So for a particular training data set, the function, the predictive function, will not be the mean function. There will be some jiggling around the mean, and that's captured by the variance. So we're integrating over this quantity the difference between the individual fitted models and the mean of these models. You take the square of that and you integrate over all input data distributions. So yeah, I also want to give you some, tell you what mathematical stuff we are using. And the first equation we already discussed. So if Z is a matrix applied to y, so Z is A times y, and we know the covariance of y, then the covariance of Z is simply A times covariance of y times A transposed. So we discussed this before. And the second equation is new, and so I'll give it to you because I'm using it. So if you have a matrix phi and you form the expression phi times phi transposed phi and the inverse of this times phi transposed. So this inverse must exist, of course. And you take the trace. The trace is just the sum of over the diagonal elements. Then this is equal to m, which is the number of columns of phi. So you find this in some formula collections, or you can derive it yourself. An easy special case would be phi is a square matrix and has an inverse. Then, of course, the phi transposed phi inverse is the same as phi transposed inverse times same as phi inverse times phi transposed inverse. So the phi's cancel and you end up with the identity, and then the trace of the identity. Obviously, I has 1 on the diagonal, and if you sum over the ones, you get the dimension m. So for this special case, it's very simple to see, but it's also true for other cases. But first, let's look at a very simple example. So y equals w naught. So it's simply a constant. So we only have the offset in the model plus epsilon. Then an unbiased estimate of w is simply the mean of the y's. So we sum over all y's and just divide it by n. And by using this variance formula, so the variance of this expression, first we have to consider that the variance of y is sigma square, because that's simply the noise variance. If we add this n times, we end up with n times sigma square. If we divide it by n, we have to divide the variance by n squared. Now this comes from this expression here. And then we end up with the variance of W naught is simply sigma squared divided by n. So that's the variance in which comes in from the uncertainty of the W naught parameter. And then we can just add the variance and the bias, the variance and the residual. So we add 1 divided by n sigma square plus sigma square, and we get the formula n plus 1 divided by n times sigma square. So the test cost average over all training data of the same size is slightly larger than sigma square, which we also expected. We can even go one step further and estimate the sigma square, and an unbiased estimate is the sum over the difference of y minus the estimate of W naught least squares, and then we have to divide by n minus 1. We discussed this before, that this is an unbiased estimate, but we defined the training error as the average of this expression, so that's why we have to multiply it by n and divide by n minus 1 times the training error of this particular data set. So that's why it's an estimate only, but it's an unbiased estimate. And if we substitute this estimate of sigma square here, we get the expression that the expected test set error average over all training data is n plus 1 divided by n minus 1 times the training error. So here you see the correction of the training error to give you a large estimate for the test error data. And the correction is n plus 1 divided by n minus 1. And later we will see that for linear model, this will be n plus number of parameters divided by n minus the number of parameters. We also can look at the biased estimate. So the model is the same as before, but now we do a penalized estimate of W naught. We don't divide by n, but we divide by n plus lambda, so this will be a little bit smaller than before. We can calculate the square of the bias quite easily. It's W naught square times lambda square divided by n plus lambda square, and this is larger than 0, so now we have a biased model. And but if lambda equals 0, then this will be 0, of course. And the variance now is, so we use the same n times sigma square, because we sum over I n times, and then we have to divide it by this term squared because of the same rule of the variance, and then we get n divided by n plus lambda square plus sigma square, which is smaller or equal than the sigma square divided by n, which was the unbiased estimate variance. And for the expected test error, average over all training data set, we simply have to add the bias square plus the variance plus the residual error. So for this very simple model, it's easy to calculate the bias and the variance. But we want to go one step further and also consider a linear model, because that's already quite interesting and powerful, because a linear model, special case would be a basis function model, which are quite useful already. And in fact, that's what we're doing. So we are considering basis functions, phi of xi. So this is a vector of basis function, times w plus epsilon I. And again, epsilon I is independent noise with variance sigma square. Just making a note here. So and the ML estimate, we know that is unbiased in this case, and we know this from lecture on least squares regression. Is phi transpose phi, the inverse of that, and phi transpose y, and we know that the bias is 0 for this in this case. And by using the rule of variance, how variance is transported, so this rule here, we can calculate the covariance of this estimate. So all of this is what is A in this equation here. So we get A, then the covariance, then A transposed, which is this expression. And the covariance of y, we know as before, they're all independent and of size sigma square. So we have the sigma square here. Then the sigma square times an identity matrix. So we can put the sigma square in front. And then we get this expression times this expression. And this cancels. So we are left with one inverse of phi transpose phi transpose phi times sigma square. And this is the well-known estimate of the covariance of W hat. We notice that this is a matrix, not just a scalar. So this is exactly the covariance matrix we are interested in for predicting the uncertainty in W hat. So now we know what the uncertainty is in the W hat is, and now we want to conclude what the uncertainty is in the prediction. Now we're not interested in the parameter uncertainty, but in the uncertainty of the prediction. So yeah, we're using the same formula again. We know the covariance of W, and now we are multiplying it by, because we've the function is the phi applied to the W, and here we are also making the approximation that we're looking that the x doesn't change in training and test, so that the empirical distribution of the x data we can use for training and test. So that's why the prediction at the same locations is simply the covariance f, the estimate W multiplied by phi. And then we are using the same rule, phi, the covariance, phi transposed. So that's the covariance, but we are only interested in the trace because we want to the average of the trace, because we are interested in the variance and not the covariance of the prediction. So now we are substituting our estimate here, which is this expression, if you remember, sigma square divided by n we're having now, and here we're having this phi transpose phi, the inverse times phi and phi transposed, and we have to take the trace of this expression. And if you remember, we said that this is simply m. So if we apply our trace rule, we get the variance estimate is the number of parameters divided by n times sigma square. Yeah, this is an important result which you see in many often applied, that this is an estimate of the uncertainty in the prediction of the model, strictly only for linear models. And the predicted variance increases if we have more parameters, which makes sense because then we have to estimate more parameters and we get more uncertainty. And it increases with n the number of training data points, which also makes sense. If you have more training data, the uncertainty in your model correspondingly decreases. So the generalization cost, the one we're interested in, average overall training data, is now the residual error, so sigma square plus number of parameters divided by n by sigma square. And this is number of parameters plus n divided by n times sigma square. Again, we see that this is larger than sigma square, and the more parameters we're having, the larger this difference is. And as before, we are now going one step further, and we are doing an unbiased estimate of the variance, which is the, as we said before, the training error. And now we don't divide it by n-1, but by n-mp. And since this is already the average, we have to multiply it by n. So n divided by n minus mp times the training error. And if we substitute that, we get a so-called ModellCP statistics. So we take the training error and we multiply it by, or the average training error, of course, it's the average training error. We multiply it by n plus mp divided by n minus mp. And this would be an estimate of the average test error. So this is one formula maybe to memorize, or it's a famous formula for estimating the test error based on the training error. And if you want to do model selection, then you take the model where this ModellCP statistics is smallest. Yeah, if we take the expectation of both sides, we can see that the expected training error, average overall training data sets, is in fact sigma square minus mp divided by n times sigma square. So it's the residual minus the variance as we discussed before. And if we look at the difference in the expectation of the training and the test error, it's 2 times. And we are considering the true sigma square. It's 2 times the variance, 2 times mp, number of parameters divided by n times sigma square. And so strictly this is only true for the squared error, but it's sort of applicable in general. If you look at these conceptual plots, and so we can now look at the different curves. So this is number of parameters, for example. The residual error is independent of the number of parameters, so that's a sigma square here. Then the variance that increases linearly with the number of parameters. So now we saw that somewhere. So here, it's proportional to mp, and the bias starts at a large value if the number of parameters is small, and then it decreases with number of parameters. So the model is able at some point to be unbiased if you have a large number of parameters. And if you're interested in the generalization error or the test set performance, you have to sum all these 3 terms. So the residual plus the variance plus the bias. And then you get this very typical curve here. So if the model is too small, the generalization is dominated by the bias. And then if you make your model larger, the bias decreases. And at some point the variance sets in, and if you make your model too complex, then your generalization error gets worse again. So you have this typical optimum here, and you would pick the number of parameters in this area somewhere to get good performance. And if you look at the training error, it's residual plus the bias minus the variance. So you see something like this. The training error always gets better and better and better, and might even be 0. And then the generalization error increases. So so definitely what is important to remember is the training error always goes down with complexity, and the test error goes to the minimum and then increases again. And you see a similar behavior if your complexity is 1 over lambda. So if lambda is small, you have a very flexible model. If lambda is large, you have a very inflexible model. Large bias, so the bias goes down, the variance goes up, the residual is the same, and you see a similar behavior in the generalization plot here, figure. So you can think of MP or 1 over lambda, or even the training epochs. Yeah, so here it says training epochs, which is also means that if you do a lot of training, many epochs, you sort of explore the complexity in your neural network. But if you do stop training, then you will be dominated by the bias and not the variance. So MP is so Mallet's MP is quite important, and it can be derived from a linear model assumption and a minimizing least squared error. So you're assuming it's Gaussian noise. There's another criterion called Archaicus information criterion, or AIC, which doesn't assume you're using the squared error cost function, but you're using a negative log likelihood cost function. So the cost is the negative of the likelihood of your model, and the log likelihood is then the sum over the log likelihoods for each individual data point, and you would minimize the negative of the log likelihood. And then the Archaicus information criterion, and I'm using the definition from Wikipedia, is minus 2 times log L plus 2 times MP. So MP is the number of parameters, and this is minus 2 times the log likelihood. And this model with a smaller AIC would be preferred. You can divide AIC by 2 times n, because this would give you would be the average log likelihood training error plus MP divided by n. So you see here that if you do the just divided by 2n, you also get the MP over n behavior here, because this is now the average training error divided by n, not average, but divided by n, whereas the Archaicus is not dividing by n. So that's why it looks similar. And you can also see that Archaicus criterion and CP are the same if have the same selection criterion if sigma square is known. So here, this is from Trevor Hasty's book, and on the left side, he uses the log likelihood loss, like as it is specified by Archaicus criterion, and you see the training error going down with the number of basis function in this case, and the test error having this minimum, and they go up as we discussed. And Archaicus really nicely matches this, and it doesn't show this extreme increase here, but if you do the selection according to Archaicus, you would be pretty much in the right spot here, where the test error is quite small. And you could not make the selection based on the training error, because the training error continues to go down. And then Hasty also checked it, how it performs if you don't use a log likelihood loss, but a 0-1 loss. And here you see that the fit is not quite as good. If you look at the test error, it's this one, and the Archaicus is here. But if you look at the minimum where Archaicus criterion is best, then the test error is also not bad. So even if the assumption that it's a log likelihood cost function is violated, it could still mean that Akaike's criterion is useful. I think that's what this plot shows here. Yeah, here's a proof of the biased variance decomposition. It's a little involved. You have to look at all these different expected values. So here's even just for one parameter, but it generalizes also to functions, which are the sum of the variances and the sum of the different terms in different locations. So if you look at this term, then now we have three terms. We have to look at bias, variance, and residual. You get these terms out from the analysis, and then you can look at the three cross terms and can see that they all become zero. So that's the reason why this bias variance decomposition is true. But it's only true strictly for the squared error cost function. So now we're looking at a Bayesian approach. So often in literature you see CP or Akaike as a selection criterion. Of course, I mean, as we discussed before, in most cases, in realistic cases, you're doing test error, training error, only if for some, now you do the empirical evaluation, only if for some reason this is not possible, because you have the data is too small to do a division into training or test, or for some other reasons you couldn't do an evaluation on a test set, then you would maybe use these selection criteria. The same is true for the Bayesian, which we are discussing now. So in principle, a Bayesian statistician wouldn't do any model selection, because he would think all models the user thinks are plausible before the user looks at the data should also have a corresponding significance after data was made available. So a strict Bayesian approach would assume there's a prior probability distribution over different model assumptions. So there could be different architectures, could be different types of models, whatever. So linear model, basis functions, neural networks, kernels. And if you do a prediction, before we always said we have to integrate over the parameters. Now we also have to sum or average over the models. So this is the posterior weight of the different models given the data, and this would be the prediction for the individual models. So we would do another averaging, not just average over parameters, but also average over the different models. Of course, this is a little bit time consuming and maybe awkward. And so even the Bayesian says maybe we should select models at occasionally for practical reasons. Let's put it this way. And so the critical term for model selection is the probability of a model given the data, and that they invert it using Bayes formula. So it's the probability of the model times the probability of the data given the model, at least it's proportional to this. And then they assume the models should all have the same prior. So then for model selection, the probability of the data given the model is the relevant part. And this is called marginal likelihood or model evidence. And it can be calculated in this way. So we have, so this is a prior, the probability of the W of the parameters given the model. This would be the prior for this particular model. And this is the likelihood, this is the probability of the data given the parameters. And then we would have to integrate out the parameters in this expression. And this is what we are now trying in a little bit, longish derivation, because we want to end up with a nice and simple expression. Of course, you can start using this formula and trying to do some sort of Monte Carlo integration to approximate this, but we want to be pretty rough and brutal and get a pretty nice simple approximation. So we are starting from the Bayesian formula for the probability of the W, the way it's given the data, is the probability of the so it should be probably conditioned on M as well. Let me make a note here. So so this would be the probability of W given the data and the model is the probability of the data given the W and the model. So we are just simply applying Bayes formula. Okay, and then the probability of the W given the model and probability of the data given the model. So we're just conditioning everything on the model. And we are interested in this term here, the probability of the data given the model. So we put this on the left side and divide it by this expression, and we get this. The probability of the data given the model is the probability of the data given the parameters in the model times the prior divided by the probability of the data of the W given the data. And so this must be true for any W. Let's also let's consider the map, W map, and take the log. So then the log of this expression here on the left side is the log of the probability of the data given the map, given the model, plus the log of the probability of the map given the model minus a log of the probability of the map estimate given the data. So the first time, this is the likelihood for the particular parameter value. This is the prior. And we can calculate them. So we have this expression, we have this expression. So we have to think about this last term. Which is a probability of the map estimate given the data. From the previous lecture, we know that this posterior for linear models and Gaussian noise is a Gaussian distribution, and the Gaussian prior, of course, is a Gaussian distribution centered at the map estimate with a covariance, which we write in this way. So the covariance is sigma squared times x transpose x. So we are using a linear model here. And using this x notation, could also have used basis functions. Sigma squared divided by alpha squared times I, and the inverse of this expression. If you're using the maximum of this expression, so map and map gives 0 in the exponent. So we are used to e to the 0 is 1, and we are left with a normalization term. So the log of the map given the data is the log of 1 over the square root of 2 pi to the power of mp, and then the determinant of the covariance of W given the data. And this is, so we have this expression, the power of minus 1/2. And then we end up with minus mp divided by 2 times log 2 pi minus 1/2 log of the determinant of the covariance of W given the data. So now we can solve or look at this expression. the log of the probability of the data given the model is the likelihood plus the prior, and then these new terms we just derived, number of parameters divided by 2 log of 2 pi plus 1/2 log of that of covariance of W given D. And now we are doing some pretty rough estimates. First of all, this expression, the log of the determinant of the covariance, can be approximated as minus the number of parameters times log n plus some constants. And the reason is that for large n, the covariance of W given the data becomes diagonal, and the diagonals become proportional to 1 over n. And thus this expression holds. And then the log is the log of MP times log n. So that's something which is, one can derive. And then the quantity we're interested in is the log, so the likelihood and the prior, and then this MP divided by 2 log 2 pi minus 1/2 MP log n plus constants. And we can see that this explains overfitting and underfitting, because if you have, so the first term might produce a better fit, but at the cost of the of a larger number of parameters. And now we are only keeping terms which depend on n. And we're using the maximum likelihood estimate instead of the map estimate. This is for historical reasons. One approximates that the log of the probability of the data given the model is the likelihood model, the likelihood of the data given the likelihood estimate. And the log of that minus MP divided by 2 times log n. So this is left over from this term. And now finally we get the final result. The Bayesian information criterion BIC is minus 2 times this expression. You can look at the definition in Wikipedia. So BIC is minus 2 times the log of the data given the maximum likelihood estimate plus number of parameters times log n. The better model would have a smaller BIC. So BIC is used also sometimes, and it's compared to AIC and often gives better results. So here I divide BIC by 2n, which would be then the average log likelihood training cost plus 1/2 MP divided by n times log n. And if I divide AIC by 2n, I get the average cost of the log likelihood of the training data plus MP divided by n. So we see the difference is essentially this factor 1/2, but then also the log n. So this penalizes more the larger n's. No, so the BIC is increasing also with log n, and not just decreasing with n. So the decrease is smaller with n. Yeah, that's it. So and the two plots which are always important. One is if you increase the number of data points, then the difference between training and test error becomes smaller and smaller. And if you increase the parameters, the difference increases. So that's what you're seeing here. If you increase n, the number of training data, the delta decreases. If you increase the number of parameters, it increases. So this was the derivation of the BIC formula, and often both are reported, and often the BIC is a little bit more robust estimate. So BIC is often preferred comparison to AIC. Okay, so this was now we had the frequentist or the classical approach with CP and AIC, and this was the Bayesian approach. Again, the results are not that different. in particular, if you make these pretty rough approximations in the BRC derivation. So finally, I want to talk about modern frequentist approaches. Briefly, just mentioning the minimum description length, or MDL approach, based on prior work from Kolmogorov and Solomonov and Chaitin, and the ideas were then extended by Risanen and Wallace and Boulton, and they introduced the principle of the minimum description length. So, and under simplifying assumptions, the MDL criterion becomes either the evidence framework or the BIC criterion. So in terms of practical aspects, I mean, they're the same, so you can take the one you prefer. But some researchers prefer to think in terms of information theory, not Bayesian price and likelihood functions. So it's a little bit a matter of taste, what you prefer. But yeah, definitely the majority is more uses a Bayesian formalism because they have a better intuition for what is going on. And then I want to talk a little bit more, but not really a lot, but a little bit more about statistical learning theory. It's in the Russian mathematicians, in the tradition of the Russian mathematicians, Kolmogorov and Glivenko, and the Italian mathematician Cantelli. And in the stricter sense, SLT was developed by Vladimir Vapnik and Alexei Chervonenkis. It's called VC theory. And the community, sometimes called COLT, or computational learning theory community. And as I mentioned before, it's similar to PIC or PAC, which stands for probably approximately correct learning, from Leslie Valiant. So I'm also just discussing the most basic variant. So there we are assuming that the data is generated by some unknown but fixed distribution, but otherwise arbitrary. So there's a function, then there's a function class we are considering. So we called them always W of X before. So it could be the class of all linear classifiers with MP equals n plus 1 parameters. And SLT consciously does not assume that the best possible, the true function or the target function f of x is contained in M, so it's independent of that. And we're also only considering binary classification without noise, which means the classes are separable by, let's say they are without noise. They're not necessarily separable, but a member of the model class. So as before, we train a random sample of P of X and Y. And SLT considers the difference between training and test as before. And here we are focusing on the misclassification cost for the evaluation. And one thing which is also specific, the difference is considered for any W, not just the W which minimizes the training data. But in reality, of course, the difference between test and train is the largest for the one which minimizes the training error. So it's really considering the same case. So these are the statements SLT is interested in. So with large probability, so 1 minus eta should be small. And for any W, the test set performance of a W should be smaller than the training plus epsilon. So of course, the test is larger than the training in general, but it's smaller than the training plus some epsilon. And then the art is to find a good epsilon. Model selection is then performed on the training error plus this epsilon. And here we're using the particular W because this difference is the largest in general for the parameters which minimize the training error, of course. So trivially, if we make epsilon very, very large, then this is true. Anything is smaller than infinite. So we want to find the smallest possible estimation of an epsilon. And in this context, the VC dimension was introduced, which for linear models, linear classifiers, is the number of parameters, so m plus 1. Just to give you a feel what this mysterious VC dimension is. In Wikipedia it says the VC dimension is a measure of the capacity or complexity or expressive power or richness or flexibility of a space or a class of functions that can be learned by a statistical classification algorithm. Yeah, and it can be finite or infinite. Some kernel approaches it's infinite, but for a linear classifier example, it's a number of parameters. So, and for systems with finite VC dimension, this bound epsilon decreases with n when n is larger than the VC dimension. Otherwise, it might increase without bound. In practice, this bound is often too conservative, so the training error plus epsilon is much larger than the average test error, which always gives you a little bit, bad feel about the validity of this estimate. But of course, they are not saying it's hitting the test error. It's saying it's bounding the test error, and as long as the minimum of this training plus epsilon is in the right location, it doesn't really matter. So just to give you a feeling for how this epsilon might look like, so here's an example. Now there's not just one epsilon. You should find one which gives you a closed bound. So epsilon, for example, can be the square root of 1 over n. So n is the number of training data. And there's a big bracket with the VC dimension. So in the simplest case, this is the number of parameters. Times the log of 2n, so 2 times the number of training data, divided by the VC dimension, plus 1, minus log of eta divided by 4. The eta was the probability you were interested in. So eta should be also a small value. So you see these expressions can be quite complicated. So you can compare SLT with a frequentist approach. SLT does not make any assumption about the true function. In a frequentist view, this could mean that the bias is large. SLT makes a statement about the worst case, the supremum. Often the supremum corresponds to a weight factor that minimizes the training cost, as I said before. But if the training data is not worst case, the training data is not worst case. They are randomly selected. So they assume to be IID distributed, identically independently distributed from a fixed joint distribution. Conclusion: machine learning focuses on generalization costs and traditionally doesn't not as much on parameter estimation, although explainable AI is gaining interest, where you're also more interested in understanding the mapping and not just the prediction error. Empirical model selection is most often used. If possible, cross-validation results should be reported. And today, often the only test set performance is reported, which I hope will change at some time in the future. So frequentist approaches trying to estimate the generalization error averaged over all models, over all possible training data sets. And we have studied CP and AIC. The Bayesian approach ideally would do model averaging instead of model selection. We derived the BIC criterion, which is useful if model selection needs to be performed. An advantage of a statistical learning theory is that the true function does not need to be included in the function class, but the derived bounds are typically rather conservative. So if you consider training error plus epsilon, this is typically much larger than the actually observed test error. But it's but SLT doesn't say that it's trying to estimate the test error. It's trying to estimate a bound, so that's understandable. But it's also, the problem is you need to learn a different mathematical theory, different from Bayesian and different from frequentist analysis. So typically involves a lot of engagement by the researcher to doing good research in this field, and then the results are often not easily applicable to real world problems. One particular thing is also that SLT has been developed in the machine learning community around 1990 plus minus, whereas frequentist and Bayesian approaches originated more in statistics. So in the there's a little bit of an appendix which discusses some properties of some cost functions and norms, if you're interested. Otherwise, this is it. So thank you very much for your attention.